Besides axes and planes, another symmetry operation is a reflection through a center of symmetry, what we call an inversion center. So if reflection of all parts of the molecule through the center of the molecule produces an indistinguishable configuration, then that center is called a center of symmetry or a center of inversion, and is then designated by the symbol I. So if you look at these two molecules, the molecule of CO2 and the molecule of benzene, we look at the center of the molecule in both cases. A reflection of the whole molecule around that inversion center would produce another version of those molecules that would be indistinguishable from the original conformation. So these two molecules have an inversion center. So I'm going to ask you now to stop the video and have a look at these four molecules and work out whether they have an inversion center or not. So do these molecules have an inversion center? Please stop the video now. So if we identify the center of the molecule in all cases, and then we think of, reflection around that center, we can see that the only one that would allow us to do a reflection through that center that would give us a configuration that is identical to the original one is in the case of the sulfur hexafluoride. In all the other cases, the cis N2F2, the molecule of silane or the molecule of hydrogen sulfide, an inversion through this center will give us configurations that are not identical, would be distinguishable, they would be different from the original one. So in this case, only the molecule of sulfur hexafluoride, which is very symmetrical, has an inversion center. Another symmetry operation is SN. The symmetry operation is a rotation about an axis followed by reflection through a plane perpendicular to this axis. So rotation about an axis followed by reflection through a plane perpendicular to this axis. So if a rotation through an axis C2, 3, 4, 5, 6 followed by a reflection through a plane perpendicular to that axis gives us a configuration that's indistinguishable from the original one. That axis is an n-fold rotation reflection axis, and we call that SN. We use the symbol SN for that. They are also called n-fold improper rotation axis. So what do we mean by that? Imagine, for example, the molecule of methane, and think of an axis that goes through the carbon and bisects the carbon-hydrogen-carbon bond angles. If you rotate the molecule through that bond 90 degrees, these two hydrogens here now become these two ones. And then if you reflect, and remember your axis is still here, and now if you reflect that molecule through a plane perpendicular to that rotation axis, you end up with your two hydrogens here now become those hydrogens here, and you end up with a configuration that is identical to the original one. So that is an improper rotation axis for methane, and in this case an S4. An S4 because it's a C4 symmetry axis. The rotation is 90 degrees. Another symmetry operator is another symmetry operations is the identity operator E, and all objects will have that. It's the simplest operator you can have. Is literally leaving the molecule unchanged, not doing anything to it, and it identifies the molecular configuration. That's the structure of the molecule. So any molecule, it doesn't matter how little symmetry, it will always have an identity operator because it will always have one configuration, whichever it is. The identity operator can also be reached by successive symmetry operations. For example, imagine the molecule of ammonia and think of a C3, a rotation, 120-degree rotation through an axis that goes through the atom of nitrogen. So if we number the hydrogens 1, 2, and 3, we do the first rotation, and your hydrogen 1 ends up here. We do another 120-degree rotation, and your hydrogen atom falls here. And then another one will put back the hydrogen atom where it was. And so 3 C3 rotations will produce the identity operator, will bring the molecule back to the original configuration. So a C6 is axis is a rotation angle of 60 degrees. A C3 is a rotation angle of 120 degrees, which would equate to 2 C6 rotations. If you do a 180-degree rotation, that's a C2. That it would be 3 times that 60-degree angle, that 3 times that 60, that's C6 axis. A rotation of 240 degrees would equate to 2 rotations around a C3 angle, or 4 rotations around a C6 angle. A rotation of 300 degrees would equate to 5 rotations around that C6 axis. And finally, a rotation of 360 degrees would be performing the rotation around this C6 axis 6 times, and that would bring you back to the original configuration of the molecule, to the identity operator. The following 3 slides are trying to summarize all the symmetry elements we have looked at in previous slides. All the molecules will have the identity operator, the E, the symmetry element none, all atoms are unshifted. It's literally the configuration of that particular molecule, and all the molecules will have one. You also have rotation axis, C2, 3, 4, 5, 6, depending on the angle of rotation, from 120 a C2 to 60 degrees a C6. You can also have mirror planes, sigmas, reflections through a mirror plane. And the molecule can have different types depending on whether they contain the principal axis, whether they are perpendicular to the principal axis, or whether they contain the principal axis and bisect 2 adjacent C2s. And we talked about sigma H, sigma V, and sigma D. Molecules can also have an inversion center, I. And finally, molecules can also have rotation reflection axis, improper axis, which is a rotation by that axis, follow to C2, 4, 5, 6, whatever integer, follow by reflection in a mirror plane, which is perpendicular to that rotation axis. And we've got here an example of S4, the molecule of ethane and staggered configuration, and S6, and even the ferrocene, you can have quite high integers, an S10.